Okay, so that's the background information. So for the constructive interference, what do we need? This path difference needs to be multiples of a full wavelength for us to be able to get a constructive interference. That's what it is. All right, so the path difference needs to be multiples of a full wavelength. So we end up getting no phase difference. Everything is going to be on top of each other. So this is going to give us a constructive interference. All right, so this is the condition for a constructive interference. So sine of this angle is going to be delta L divided by D. All right, so at this angle, we're going to end up getting constructive interference patterns. Okay, so N could be 1, 2, 3, and so forth. All right, and this is going to be your first constructive interference, second one, and the third one. Now, for the destructive interference, what needs to happen is the path difference has to be off by a single wavelength. All right, so if you introduce a path difference, which is off by a single half a wavelength, all right, so which means that we're introducing a single half a wavelength difference between two lengths. And if that's the case, this is going to give us a destructive interference pattern. All right, so that's it. So the idea is straightforward. Okay, let's take a break for 10. Be back within 10. All right, so double slit experiment. So we're going to end up getting these constructive and destructive fringe patterns on the screen. And obviously, what's causing the fringe pattern is the interference of light from two different sources that we're looking at. So if this path difference that you're looking at, if it's multiples of a single wavelength, then you will get a constructive interference pattern. And if the path difference is off by half a wavelength, then you're going to end up getting a destructive interference pattern. That's it. So that's the entire story. Now we have to express everything in terms of the distance to the screen. L is going to represent the distance to the screen. And the letter Y is going to represent the distance from the center, from the central fringe to the interference pattern that we're looking at. So we got L, so that's the distance to the screen, and then the letter Y is going to be the distance with respect to the central bright fringe to the other fringe patterns. All right, so which means that we will have to do the derivation a little bit more sophisticated to serve our purposes. So now we will have to just include the experimental setup into it. So D is going to be the slit separation once again. So which means that we're looking at the separation distance between the two slits. All right, so delta, lowercase delta that we're looking at is going to be the path difference. So once again, we're changing notation. So R2 is the length that this ray is going to travel. R1 is the length that the other ray is going to travel. L is the distance to the mirror, the distance to the screen, not the mirror. All right, so the lowercase y is going to represent the distance between the fringes to the central fringe. And that's it. All right, so it says bright fringes, but you can use it in terms of any fringe that you're looking at. All right, so we're modifying the mathematics, so we will include the experimental setup into it. So lowercase delta is going to represent the path difference. Okay, if you want to get a constructive interference, obviously, path difference needs to be the multiples of single full wavelengths for constructive interference. All right, so we'll express this sine of the angle is going to be delta divided by D. So the delta is going to be, once again, it has to be the same as the multiples of full wavelengths. All right, so we got a second triangle here. All right, so the second triangle is going to involve the length to the screen and the letter Y, distance between the fringes. Okay, notice that this time the angle that we're looking at, theta, the same angle could be expressed in terms of a tangent. All right, so opposite over the adjacent. All right, so the tangent is the same as sine of theta divided by cosine of theta. All right, now we will employ a trick. All right, guys, these angles that we're looking at are extremely small angles, so which is going to allow us to use small angle approximations. All right, so sine of theta in terms of small angle approximations can be approximated as a theta. The cosine of theta is going to be approximated as 1. All right. If you haven't seen it already in calculus, you will see it at some point when you guys are taking more advanced math courses. So small angle approximations can be used, obviously, when the angles are extremely small. So sine of theta is going to be theta, cosine of theta is going to be 1. So which means that tangent of theta can be roughly about theta, which means that tangent of theta is going to be the same as sine of theta, which is going to be the same as theta. So all three will be the same. So this is going to allow us to relate two triangles to each other. All right, so sine of theta from the first triangle and the tangent of theta from the other triangle means that those two equations will be equal to each other. All right, so you end up getting this from the sine of theta, all right, and you end up getting this from the tangent of theta. All right, so using small angle approximations, we can make them equal to each other. All right, so isolate the letter Y. So this is going to be the distance to the fringes that you're looking at with respect to the central fringe. All right, so we end up coming up with an equation. All right, so now let's apply this to problem number 1 from the handout. All right, so let's pause here and then read through. Okay, so our light source is going to be red. I'm assuming that we're using laser in this case. All right, so it has a known wavelength. It's expressed in terms of nanometers, so that's 10 to the minus 9 meters. And we are given this slit separation. So D is going to be this distance. D is the slit separation. Screen is going to be located at a given distance. L is going to be that distance. So what it says, find the distance, which is the letter Y, between the central bright fringe, which is going to be M equals 0, to the third order bright fringe. So the third order bright fringe means that you're looking at the third bright fringe. This is 0, there's going to be 1, there's going to be 2, and this is the third bright fringe that we will be looking at. All right, a couple of things regarding this. All right, your tests are getting slightly better. And some of you guys are doing the work right and still losing points because you're not showing enough work. And this time, the timing is not a problem because I'm giving you guys about 30 minutes. All right, so here's what I'm looking for in terms of doing these problems. Number 1, list everything. All right, so the wavelength is given. I'm expressing in terms of meters. All right, do your conversions. Distance is given, so this is fine, expressed in terms of meters. Separation distance between the slits as well as the screen is also given. All right, so look for the distance between the central fringe and the third order bright fringe. That's what we're looking for. All right, so whenever you're solving a problem, you have to solve the problem using what's given to you. These are known as the initial conditions. All right, so the letter Y is what we were looking for. I don't like the way I've done this problem because evidently I know what it's supposed to look like, so I make an assumption here. Normally, what I'm looking for whenever you guys are solving a problem, you need to justify the initial formula. Okay, I cannot justify the initial formula here. That's what I don't like. More than likely, I end up solving it by using, this must be an example in one of the books. All right, this is not the way I would do a problem normally. All right, so what I'm doing is I'm isolating theta. And then what I'm trying to do is I'm going to try to relate this to the distance that I'm looking for. Okay, so the way, this is a backward ass way of solving a problem in reality. All right, so I know the theta. I know that this theta is going to be related to this theta. And from that, I'm going to be able to figure out what this distance is. And the only way you can do the problem backward like that is if you've done a problem like this a million times and you kind of know how things are going to go, right? I don't like to solve problems like this usually. All right. So these angles are going to be the same. So, all right, so solve for the letter Y. And then substitute this angle into that one. Okay, that's it. All right, that's as far as this goes. Okay. Normally, the way I would have done it is this would have been the starting point. All right, I would justify it because I'm looking for Y. And then the angle would be missing here. Obviously, I would go back to that formula and then figure out theta and then plug it in. All right, and instead of using this, I would have used small angular approximation. This is a brute force method. It's going to work the same. It doesn't matter. All right, so plug the numbers in and everything works out. So this will be the distance to the third fringe. All right, so this was an example of how to do this stuff and what not to do. All right, so this is problem number 2. The one that you guys will get to do is very similar to problem number 1, except now we will have 2 different light sources, 2 different wavelengths. Okay, so we will have a single light source. It's going to be composed of 2 different wavelengths. Okay, when you have 2 different wavelengths, what do you guys think? What do you think is going to happen? All right, let's have a conceptual discussion. When you have 2 wavelengths, when you have a light source with 2 different wavelengths, when you look at the fringe pattern, what do you guys think you're going to see? Any ideas?
It won't be as evenly spaced, I guess.
Okay, yeah, I'm gonna give you 5 points for participating in this one. Okay, guys, the wavelengths are slightly different, so their maxima as well as their minima are not going to be coincident, right? They're not going to be on top of each other. They will be slightly next to each other. That's what it means when you do actually look at this screen. All right, problem number 2 is exactly like problem number 1, except this is your homework. Just work on it. And if I'm up to it, then I'll probably make it a test question. Okay, the other thing that I want you to notice is take a look at the intensities, the brightnesses or the intensities of these fringe patterns. Notice that the central one is the most intense, and then it starts to get dimmer and dimmer and dimmer. All right, so what's the explanation for it? intensity distribution. That's what it's called. So the intensity is the same as brightness of the distribution. Central fringe is going to be the most intense, and then the intensity starts to diminish as you start to get away from the central one. All right, central one, that's the zeroth fringe. All right, so N0 is the first one, M1 is the, N0 is the central one, M1 is the first one after the central one, and so forth. So intensity is going to diminish. All right, let's come up with a mathematical formula. Obviously, what's happening is now the phase angle is going to matter. All right, so you don't get perfect cancellations and you don't get perfect reinforcements. All right, speaking of intensity, this goes back to the electromagnetic wave theory. We have an expression for intensity. Remember the electromagnetic wave in terms of its RMS value. When you square it, the intensity is going to be proportional to it. All right, so the derivations and everything else was on the video that I posted. Now, so we have to come up with an expression for total intensity at the screen. So we got two slits, which means that we will have two electric field components from this. All right, notice that both of them are going up and down. Both of them are waving up and down at the same rate, except there's going to be a phase difference between these two. So they're not going to be 100% in phase. All right, so let me try to explain this. All right, this one that you're looking at, this is doing this, it's going up and down. I'm talking about this one. All right. The other one is doing the same thing, except it's not exactly in phase with this one. It's going to be slightly out of phase. It's doing the same thing. All right, they're not exactly lined up. So this is the phase angle between these two. All right, so they are not slightly out of phase. That's what we mean when we say there's a phase difference between those two. All right, so this is known as the phase angle, which means that one of them is slightly offset with respect to the other one. Okay, this RMS value that we're looking at is going to be the total, the summation of these two, the total net electromagnetic, the electric field component we're looking at. So we have to sum them up. All right, so we do the substitutions. And then this is the reason why mathematics, the algebra, trig, calculus, everything becomes required. So when you add up sine of alpha to sine of beta, all right, so you have to use a mathematical identity, the trig identity function. So we have to add them up in this fashion. So this is going to get added onto that one. So it's going to be 2 times E naught. E is going to represent the amplitude of the electric field. So it's going to be 1/2 sine of this plus whatever the expression inside that is. So just add them up. All right, times cosine of 1/2 of this minus that expression. Okay, man, I was able to get it right. All right, so these two will add up to, it's going to be 2 times that expression. These two will cancel. All right, and now get rid of the parentheses here so we can distribute this. These twos will cancel.
Why is the second phase angle beta over 2?
It's not. Oh, shit. It's 100% not. Or give yourself 5 points. Okay, I was supposed to edit that out. Okay, hold on. I don't know. Man, you read my mind. It's not. Okay, so it's theta. All right, give yourself 5 points for noticing it. Because evidently I was looking at it and I say, in my head, evidently something happened. All right, so you end up getting a cancellation. 2's will cancel, so this is going to get divided by 2. All right, this is good. All right, cosine. I'm going to leave the negative there, but I want to make a point at this point. Guys, cosine versus sine. Cosine is known as an even function. So this is known as an argument. The second known as an argument, anything that has an angle in it like that. If it's a negative, because it's an even function, negative of an even function is going to be a positive function. So, which means that you can get rid of the negative. These are the things that you will get used to eventually when you guys start taking more advanced math courses. All right, so, okay, so this expression is reduced to this one. All right, so here's what I'm going to do. So here's the wiggly part. This is the sine wave. And some kind of a phase angle is introduced to it. So when you look at the total electric field, it's going to wave up and down, including this. And then this is going to have its amplitude. And amplitude is going to shape like this. All right, I'm going to make this the amplitude term. So I'm going to move this up front. All right, so this, what this says is the electric fields, the amplitude, maximum amplitude of the electric field is going to depend on the phase angle or the phase difference between these two waves. That's what it is. So this term that you're looking at is going to give us the maximum amplitude of the electric field. All right, this is the only thing that we're interested in because the intensity is going to be related to this term. And the intensity is going to depend on the phase difference between the incoming waves. All right, so I'm expressing this in terms of the maximum electric field amplitude